November 1942, North Africa. A German intelligence officer stared at the burned-out hulk of a Panzer III, its side armour punched through like paper. The entry hole was impossibly small, barely larger than a man's fist. The exit wound told a different story. A gaping cavity where molten metal had erupted outward, taking 3 crew members with it. "What kind of artillery did this?" he demanded. The surviving tank commander, his face still blackened from smoke, shook his head slowly. "No artillery, Herr Hauptmann. A single American soldier, carrying a tube on his shoulder." This couldn't be real. Individual infantry didn't destroy tanks. That's not how warfare worked. Tanks were mobile fortresses, immune to anything a foot soldier could carry. The entire doctrine of armoured warfare depended on this fundamental truth. But the evidence was undeniable, and somewhere in the Tunisian desert, American forces had left behind something that would change everything the Germans thought they knew about infantry weapons. The recovery came 3 days later. A German patrol, combing through a hastily abandoned American position near Tabourb, found it partially buried in a foxhole, a strange tube-like device, roughly 5 feet long, with a crude wire mesh sight and what appeared to be electrical connections near the grip. Leutnant Werner Osenberg, a mechanical engineer conscripted into ordnance recovery, held the device carefully. It was surprisingly light, maybe 15 pounds. The construction was almost insultingly simple: sheet metal, basic wiring, a wooden shoulder rest that looked like it had been carved in someone's garage. "This destroyed a Panzer?" his sergeant asked skeptically. Osenberg examined the bore, 60 millimeters, maybe slightly larger. The rear was completely open, no breech mechanism, no recoil system, nothing that resembled conventional artillery. His engineering mind raced through the impossibility of what he was holding. "If this is what I think it is," he said slowly, "the Americans have figured out something we've been trying to solve for years. They found 2 of the projectiles nearby, still in their fiber tubes. These were even more bizarre rocket-shaped munitions with fins, each weighing about 3.5 pounds. The warhead design was unmistakable. Shaped charge technology. But shaped charges required precise positioning, standoff distance, and stability to function. Firing one from a handheld tube should be impossible. The report went up the chain immediately. Within 48 hours, the tube and projectiles were on a transport plane to Germany, marked with the highest priority designation. By the time they need. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Reach the Kummersdorf proving ground outside Berlin. Every major weapons development agency in the Third Reich wanted access. The conference room at Kummersdorf was packed. Representatives from the Heereswaffenamt, Army Weapons Office, engineers from Rheinmetall, observers from the Waffen-SS Technical Division, and a dozen specialists in artillery and explosives. On the table between them, the captured American tube weapon. Oberst Friedrich Halder, Chief of Anti-Tank Weapon Development, spoke first. "Gentlemen, I've reviewed the field reports from North Africa. If they're accurate, and I stress if this device represents a fundamental breakthrough in portable anti-tank capability, I've asked our team to provide preliminary analysis." Osenberg, now wearing his civilian engineering credentials, stood. "Herr Oberst, with respect, the field reports don't fully capture how revolutionary this weapon is. May I demonstrate the basic principle?" He picked up the tube. "This is a recoilless rifle, except it's not a rifle at all. It's a rocket launcher. The projectile is self-propelled. The tube is simply a guide and aiming device. When the electrical trigger is pressed, it ignites a small charge in the rocket motor. The rocket begins accelerating while still in the tube, but the majority of propulsion occurs after it leaves the muzzle," a Rheinmetall engineer interrupted. "Impossible. A rocket lacks the stability for accurate fire, and a shaped charge warhead requires precise standoff and perpendicular impact to function. A tumbling rocket would be useless. Which is why they solved it with these." Osenberg held up one of the captured projectiles. These fins stabilize the rocket in flight. The warhead has a piezoelectric impact fuse that detonates regardless of angle of strike, and the shaped charge cone is protected by this conical cap, which provides standoff distance on impact. But here's what's truly brilliant. Because there's almost no recoil, the rocket's thrust is balanced by the exhaust venting from the rear a single soldier can carry and fire. This weapon, no crew needed, no artillery support, an infantryman becomes a tank killer. The room erupted in objections. The blast from the rear would kill the operator. The rocket would lack accuracy beyond 50 meters. Shaped charges don't work on sloped armor. The electrical firing system would fail in field conditions. Halder raised his hand for silence. These are all valid concerns, which is why we're going to conduct live fire tests. I want to know exactly what this weapon can and cannot do, and I want to know if the Americans have solved problems we haven't. The test range was set up with captured Soviet T-34 hull sections at various distances. German engineers had been trying for months to develop an effective man-portable anti-tank weapon. Their best effort, the Panzerschreck 41, was a specialized anti-tank rifle that weighed 35 pounds and could barely penetrate 50 millimeters of armor. This American tube weighed 15 pounds and allegedly could penetrate much more. They mounted the captured bazooka on a test fixture. Safety protocol demanded they fire it remotely first. Nobody was willing to shoulder fire an unknown weapon that might explode or incinerate the operator. Electrical leads ran back to a protected bunker. Target distance, 50 meters, the range officer announced. Hull armor, 45 millimeters, standard vertical mounting. The countdown proceeded. At 0, they pressed the contact. The effect was instantaneous and shocking. A flash from the rear of the tube, not an explosion, but a directional exhaust plume. The projectile emerged with a whoosh rather than a bang, trailing a thin stream of smoke. Even watching through binoculars, the engineers could see the rocket motor ignite fully once it cleared the tube, accelerating the projectile rapidly. Impact came less than a second later. The shaped charge detonated with a sharp crack. When the smoke cleared, the T-34 hull section had a perfectly circular hole, punched through it. The penetration was complete, clean, and devastating. The armor on the far side showed the characteristic scabbing effect, where molten metal had sprayed into the interior. Silence in the bunker, then controlled chaos as everyone spoke at once. Measure that penetration depth. What was the standoff distance? Did you see the rocket stability? Almost no deviation. The operator position, there's no visible blast damage. Halder walked down to the firing position personally. The ground behind the tube showed scorch marks extending about 15 feet, but nothing catastrophic. A soldier with proper training could have fired this from a foxhole or kneeling position without injury. He returned to the bunker. Test it at 100 meters, then 150. The results were consistent. At 100 meters, the projectile struck within a foot of aim point and achieved complete penetration. At 150 meters, accuracy degraded slightly, but penetration remained devastating. That evening, the engineering team gathered to analyze the data. Osenberg had spent hours measuring, calculating, and comparing the bazooka's performance to German weapons development. The shaped charge is relatively conventional, he explained, sketching on a chalkboard. Copper cone, explosive cavity, impact fuse. We understand this technology, but the Americans have refined the design to be much lighter and more compact than our versions. Their cone geometry is nearly optimal. He drew another diagram. But the real breakthrough is the delivery system. This rocket motor, he held up the dissected projectile, provides approximately 3,000 feet per second muzzle velocity equivalent, but achieves it through sustained acceleration rather than instantaneous explosion. This means the tube doesn't need to contain pressure, no breech block, no recoil mechanism, no heavy barrel. A Wehrmacht ordnance officer studied the numbers. What's the penetration capability against standard armor? Based on our tests and the warhead geometry, we estimate approximately 80 to 100 millimeters of homogeneous steel plate. That's enough to penetrate the side armor of any tank currently in service, ours or the Soviets. The frontal armor of a Tiger would survive, but everything else is vulnerable. The implications sank in slowly. So an American infantry squad, Halder said carefully, could be carrying 4 or 5 of these weapons. No artillery support needed, no anti-tank gun to position, just individual soldiers who can knock out tanks from covered positions. Correct, Herr Oberst. And our infantry has nothing comparable. Correct. Halder looked at the captured bazooka. How quickly could we develop something similar? Osenberg hesitated. The concept is straightforward. The execution is brilliant. Every component is optimized for field use, waterproof electrical system, simple sights, foolproof operation. This isn't a prototype. This is a refined, production-ready weapon. They've already solved all the problems we're just discovering. He gestured to the dissected rocket motor. This propellant composition alone will take us months to reverse engineer. The shaped charge geometry is years ahead of our current development, and they've clearly conducted extensive field testing to verify reliability. Give me an estimate, Herr Osenberg. To develop an equivalent weapon, properly tested, 12 to 18 months. To rush something into production, 6 months, but it will be inferior and potentially dangerous to the operator. The official Waffenamt report, filed the 15th of December 1942, was a masterpiece of technical understatement that barely concealed the panic beneath. Assessment of captured American anti-tank rocket launcher. The weapon designated Rocket Launcher M, won by American forces, represents a significant advancement in portable anti-armor capability. Key findings: penetration performance. Achieves 18,100 millimeters. Penetration against homogeneous steel plate at ranges up to 150 meters. This exceeds all current German man-portable anti-tank weapons. Operational simplicity. Weapon can be operated by minimally trained personnel. No crew-served requirements. Reload time approximately 10 seconds. Manufacturing assessment. Construction utilizes basic materials and simple manufacturing processes. Suitable for mass production. Estimated American production capacity. Thousands of units per month. Tactical implications. This weapon fundamentally alters infantry armor engagement doctrine. Enemy infantry must now be considered a primary threat to armored vehicles at ranges where they were previously considered ineffective. Recommendation. Immediate priority development of comparable German system. Current German anti-tank rifle program should be considered obsolete. The final sentence was added by Halder personally. The Americans have achieved what we believed impossible, giving individual infantrymen the power to destroy tanks. This changes everything. The most revealing document never made it into the official files. Osenberg's personal notes, discovered decades later, contained this entry. We've been approaching this problem wrong. We assumed anti-tank weapons needed to be powerful, which meant heavy. Complex recoil mechanisms, crew-served weapons, artillery pieces that happened to be pointed at tanks. The Americans asked a different question. What's the minimum weapon that can kill a tank? And they built exactly that. Nothing more, nothing less. The tube could be cheaper, it's a seamless steel pipe with basic sights. The rocket could be simpler, it's barely controlled flight. The warhead could be refined, the shaped charge geometry isn't optimal by theoretical standards. But none of that matters. Because it works. It works reliably. It works in the hands of regular soldiers. And it works well enough to destroy any tank we can field. This is engineering genius, knowing what you can compromise on and what you cannot. The Americans compromised on everything except the one thing that mattered: can it penetrate armor? Everything else is subordinate to that single requirement. We would never have built it this way. We would have made it more sophisticated, more precise, more theoretically perfect. And it would have weighed 40 pounds and cost 3 times as much and been available in 1/10 the numbers. They built a weapon. We would have built a technical achievement. There's a lesson here we're not learning. That lesson would cost the Wehrmacht dearly in the years ahead. January 1943. The Führer's headquarters at Rastenburg. Adolf Hitler held the American bazooka in his hands, turning it over with the fascination of a child, examining a new toy and the fury of a man who had just learned his enemies possessed a decisive advantage. "This changes nothing," he declared, his voice tight. "German engineering is superior. We will build something better." Halder, summoned to brief the Führer personally, chose his words carefully. "Mein Führer, the American weapon is effective precisely because it is simple. To build something better may actually result in something less useful." Hitler's eyes narrowed. "You're suggesting we cannot improve on American engineering?" "I'm suggesting, mein Führer, that in this case the Americans have optimized for the correct variables. They've created a weapon that— I don't want excuses, Oberst. I want a German weapon, a superior German weapon. If a democracy of mongrels can build this, the German Reich can build better. You have 4 months. 4 months. Halder knew it was impossible. The American bazooka represented years of development, testing, and refinement. But arguing with Hitler was more dangerous than failing to meet an impossible deadline. Jawohl, mein Führer. The development program officially designated Raketenpanzerbüchse 54, but quickly nicknamed Panzerschreck tank, terror, proceeded at breakneck pace. 3 design teams worked simultaneously, each attempting to reverse engineer and improve upon the American design. Osenberg led Team A, which advocated for a near-direct copy. The American design works. Every deviation we introduce adds risk and delays production. Team B, led by Rheinmetall engineers, wanted to improve everything. Larger warhead, better sights, improved rocket motor, reinforced tube. Team C, from Krupp, proposed an entirely different approach. A recoilless rifle firing a fin-stabilized projectile, powered by conventional propellant rather than a rocket motor. The rivalry was intense and, at times, bitter. "You want us to admit German engineering is inferior?" the Rheinmetall lead engineer demanded during one heated meeting. "To simply copy an American weapon?" Osenberg's response was blunt. "I want us to admit that time matters. The Americans are producing thousands of these weapons right now. Every month we spend improving. The design is another month our infantry faces tanks armed only with rifles and grenades. But Rheinmetall's political connections were stronger. Their enhanced design won approval, despite Osenberg's warnings. The Rheinmetall design was, on paper, superior in every measurable way. Tube diameter increased from 60 mm to 88 mm, allowing a larger warhead. Projectile weight increased from 3.5 pounds to 7.3 pounds, carrying nearly twice the explosive. Penetration capability. Theoretical maximum of 160 mm, double the American weapon. Sighting system, optical rather than wire mesh, providing better accuracy. Range, extended to 200 meters effective range. On paper, it was magnificent. In reality, it was a disaster. The larger tube meant the weapon now weighed 24 pounds, still man-portable, but significantly heavier than the American version. The heavier projectile required a more powerful rocket motor, which generated substantially more exhaust blast. Early test firers suffered severe burns, despite wearing protective gear. The optical sights fogged in cold weather and were damaged easily in combat conditions. The increased range was theoretical under field conditions. Hitting a moving target beyond 150 meters was nearly impossible. Most critically, the complexity of manufacturing meant production rates were 1/3 of initial projections. Osenberg watched the test firings with mounting frustration. We've built a better weapon that nobody can use effectively, and we can't produce in adequate numbers. The Americans have a weapon that works well enough, and they're making tens of thousands. The Rheinmetall engineer bristled. The penetration capability is meaningless if soldiers can't fire it without burning themselves, Osenberg snapped. The Americans understood something we didn't. Adequate performance available in quantity beats superior performance available in scarcity. The first Panzerschreck units reached the Eastern Front in summer 1943, just in time for the Battle of Kursk. The results were mixed at best. Unteroffizier Klaus Weber, assigned to an anti-tank squad, recorded his first experience with the weapon. They told us this was Germany's answer to the American rocket launcher. They showed us the penetration figures impressive on paper. Then we tried to fire it in combat. The exhaust blast was tremendous. Even with the protective shield, the heat was dangerous. My gunner suffered minor burns during our first engagement. The smoke signature revealed our position instantly. 3 Soviet tanks immediately turned their attention to us. We managed one hit before being forced to displace. The hit was effective, I'll grant that. We penetrated a T-34's side armor and achieved a catastrophic kill, but the Americans could fire their weapon from any position. We needed specific terrain, adequate cover from the backblast, and protective equipment. These requirements made tactical employment difficult. Concerns. The Panzerschreck was powerful, but the operational requirements constrained its effectiveness. Soldiers wanted something they could fire from a window, a foxhole, or while partially concealed. The Panzerschreck's exhaust blast made such positions suicidal. By October 1943, the complaints from the front had reached crisis levels. The Waffenamt convened an emergency conference to address the Panzerschreck's problems. Add a blast shield, suggested one engineer. Protect the operator from the exhaust. Tests proved this reduced burns but increased weight to 30 pounds. Mobility suffered. Modify the rocket motor to reduce exhaust temperature. This worked, but penetration dropped by 20%, still superior to the American weapon. But the trend was concerning. Improve the sighting system to work in field conditions. The optical sights were abandoned in favor of simpler iron sights, essentially copying the American approach after wasting months on a superior system. Simplify manufacturing to increase production. This meant abandoning several refinements, again moving closer to the American design they'd initially rejected. Osenberg attended these meetings with barely concealed bitterness. We've spent 9 months learning lessons the Americans already knew. Every improvement we're now removing was something I argued against from the beginning. Halder, now a general, and dealing with increasingly desperate equipment shortages across all fronts, was more pragmatic. Can we produce an effective weapon in adequate numbers? If we simplify further, yes, but it will be essentially a larger version of the American Bazooka with all the disadvantages that implies. Then do it. Perfect is the enemy of good enough. While the Panzerschreck program stumbled, a parallel development succeeded beyond all expectations, though it learned different lessons from the captured Bazooka. The Panzerfaust took the American concept and simplified it even further. Instead of a reusable launcher and separate projectiles, the Panzerfaust was a single-shot disposable weapon. The tube was cheap steel, the warhead was large but crudely manufactured. The propellant was a basic black powder charge, rather than a sophisticated rocket motor. Preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video, it means a lot to us. Now back to the story. It was inaccurate beyond 60 meters. It had no sights worth mentioning. It looked like something welded together in a basement workshop. It was also cheap, simple to manufacture, required minimal training, and could be produced in vast quantities. By late 1944, German factories were churning out hundreds of thousands of Panzerfausts. The irony wasn't lost on Osenberg. The Americans taught us that simplicity beats sophistication, but we only learned the lesson halfway. The Panzerfaust proves we could have gone even simpler. If we'd focused on effectiveness, rather than engineering elegance, we could have armed our infantry with tank-killing weapons a year earlier. By early 1944, German military intelligence had gathered substantial information about American bazooka employment in Italy and the Pacific. The reports made for sobering reading. Production numbers. American factories were producing approximately 30,000 bazookas per month, with projectile production in the millions. Distribution. Every American infantry company had multiple bazooka teams. Some units had one per squad. Training. Basic bazooka operation was part of standard infantry training. Specialized courses lasted only 3 days. Effectiveness. American forces were routinely engaging German armor at ranges German anti-tank rifles couldn't reach, with weapons light enough to be carried by individual soldiers. The most damning report came from an interrogated American soldier captured in Italy. The bazooka? Yeah, they gave us a couple hours of training. Point it, press trigger. Don't let anyone stand behind you. That's basically it. We knocked out 2 Panzer IVs last week. The thing's not perfect, sometimes rockets are duds, but it's nice knowing we have something that can hurt their tanks. A couple hours of training to create tank killers. The Americans had democratized anti-tank warfare. By late 1944, the production statistics told the story. American M1, M9 bazooka. Total production, approximately 470,000 units. Projectile production, over 15 million production cost per unit, approximately $30. Average manufacturing time, 3 to 4 hours German Panzerschreck. Total production, approximately 314,000 units. Projectile production, approximately 2.3 million production cost per unit, approximately $75. Average manufacturing time, 8 to 10 hours. The Americans had produced more weapons, faster, cheaper, and because the bazooka was lighter and simpler to use, they could distribute them more widely through their forces. A German ordnance officer's report summarized the situation bluntly. The Americans have achieved better results through inferior engineering. This should be impossible, yet we see the evidence daily. Their weapon is less powerful, less accurate, and less sophisticated than ours. Yet they have more of them, in more places, in the hands of more soldiers. In warfare, quantity has a quality all its own. Perhaps the most revealing document German intelligence captured was a US Army training manual for the M1 bazooka. It was shockingly simple, 30 pages, with large illustrations, written at an 8th grade reading level. Osenberg studied it carefully, making notes in the margins. Section on aiming. Point tube at target. If target is moving, aim slightly ahead. This is their entire ballistic calculation guide. No range tables, no windage correction, just point and shoot. Section on maintenance. Keep dry. Clean after firing. Replace damaged parts. No complex disassembly procedures. No specialized tools required. Section on troubleshooting. If weapon fails to fire, check battery and connections. If still fails, use another weapon. They expect failures. They plan for it. The entire philosophy is different. This manual assumes the operator is a regular infantryman, not a technical specialist. It assumes some weapons will fail in the field. It assumes rough handling and imperfect conditions. And it designs around all of these assumptions. We design weapons for ideal conditions and trained specialists. They design weapons for terrible conditions and average soldiers. Under combat conditions, their approach is superior. By March 1945, with the war clearly lost, Halder met privately with Osenberg at a military hospital where both were recovering from injuries sustained during the growing Allied bombardment. "You were right," Halder said simply. "We should have copied their design directly." Osenberg nodded slowly. The bazooka wasn't just a weapon. It was a philosophy. Build something good enough, make enough of it, get it to soldiers who need it. We tried to build something perfect, and we ended up with something adequate that arrived too late in insufficient numbers. The Führer wanted German superiority, and we gave him German sophistication instead. There's a difference. Halder was quiet for a moment. For what it's worth, I read your dissenting reports. They were correct about everything. If I'd had the courage to push harder, we both know how that would have ended, Osenberg interrupted. You'd have been removed, and someone even more eager to please would have taken over. The problem wasn't the engineering. It was that we couldn't admit when someone else had a better answer. The Americans will win this war, Halder said. It wasn't a question. Yes, not because their weapons are better, though the bazooka certainly is, but because they build what works, and they build enough of it. We built masterpieces. They built solutions. September 1945. The war in Europe had been over for 4 months. In a converted gymnasium in Frankfurt, now serving as the headquarters for the US Army's Technical Intelligence Division, captured German weapons engineers sat at makeshift desks, writing reports. The victors wanted to understand everything: German jet technology, rocket development, advanced optics, all the fields where German engineering had excelled. But they also wanted to understand the failures, and the bazooka program represented something unusual, a case where American simplicity had proven superior to German sophistication. Colonel James Thompson, a career ordnance officer, interviewed Osenberg personally. The conversation was conducted in German. Thompson's family had emigrated from Bavaria 2 generations earlier, and he spoke the language fluently. "Help me understand something," Thompson said, gesturing to the stack of German technical reports on the Panzerschreck. "You had our weapon in late 1942. You reverse-engineered it completely. You had the industrial capacity and technical skill to build an exact copy. Why didn't you?" Osenberg chose his words carefully. He was no longer a combatant, but the psychological weight of defeat colored everything. "May I speak frankly, Herr Oberst? That's why I'm here. We didn't copy your weapon because we couldn't admit it was good enough. German engineering culture demands optimization. We see a functional design and immediately ask, how can we improve this? Make it more powerful, more accurate, more sophisticated. This instinct served us well in many fields: optics, precision machinery, advanced chemistry." He paused. "But it failed us with the bazooka, because your weapon wasn't a prototype. It was already optimized for different variables than we initially recognized." Thompson leaned forward. "Explain." Osenberg pulled out a battered notebook, his personal engineering diary from the war years. "Your bazooka optimized for field utility. This is a different goal than maximizing penetration or accuracy. Let me illustrate." He sketched 2 curves on a piece of paper. "Imagine this axis represents weapon capability, penetration, power, accuracy, range. This axis represents ease of use, reliability, and production cost. For most weapons, improving capability requires sacrificing ease and cost. There's a trade-off curve." His pencil moved. "German engineers typically push as far along the capability axis as possible, accepting the costs. The Panzerschreck was designed to maximize penetration. It achieved 160 mm, far superior to your bazooka's 100 mm. "But?" Thompson prompted. "But the operational costs were severe, heavier, more complex, dangerous backblast, lower production rates. These costs reduced effectiveness in the field despite superior theoretical performance." He drew another point on the graph. "Your bazooka sits here lower on the capability axis, but much better on the utility axis. The total effectiveness capability, multiplied by utility, multiplied by availability, was higher." Thompson studied the diagram. "We call it satisficing, achieving satisfactory performance rather than optimal performance. If 100 mm of penetration is enough to defeat most enemy armor, going to 160 mm provides minimal real benefit. But if doubling the penetration makes the weapon harder to use and produce, you've made a bad trade. Precisely. And this was clear in your operator manual, the document that perhaps taught us the most. Osenberg produced a worn, coffee-stained copy of the US Army's Bazooka Field Manual. This is probably the most important document I read during the war, not for what it says, but for what it represents. He flipped to a random page, a simple illustration showing the correct firing position. This manual assumes the operator has limited education, limited training time, and will be using the weapon under extreme stress. Every instruction is simple, every diagram is clear, every procedure has a backup. Thompson nodded. The rule of 3 in American training doctrine. Tell them what you're going to tell them. Tell them what you told them. Repeat critical information 3 times in different ways. We wrote technical manuals as if the reader were another engineer. Complex terminology, precise specifications, detailed procedures. Your manual is written for an 18-year-old farm boy who's never held anything more complicated than a rifle. Most of our soldiers were 18-year-old farm boys, Thompson said, simply. And that's brilliant. You designed the weapon and the training for your actual army, not an idealized army of technical specialists. We designed for the soldiers we wished we had. You designed for the soldiers you actually had. Thompson moved the conversation to manufacturing. Our reports indicate the Panzerschreck required substantially more machine time to produce. Why? Tighter tolerances, Osenberg replied, immediately. Better materials, more sophisticated components, all the things that make German engineering famous. He pulled out a cross-section diagram of both weapons. The Panzerschreck tube required seamless steel pipe drawn to precise specifications. The electrical firing system used high-quality waterproof components. The sights were optical instruments of considerable precision. And ours? Your tube was basic welded steel, good enough to handle the minimal pressure, over-engineered for durability. Your electrical system was crude but reliable, heavy-gauge wire, simple contacts, standard batteries. Your sights were bent wire. Bent wire? It was. He paused, searching for the word, offensive to engineering sensibility. Thompson laughed. But it worked. It worked, and more importantly, a semi-skilled worker could assemble a bazooka in 3 hours. Our Panzerschreck required skilled machinists and 8 to 10 hours of assembly time. When you're trying to arm millions of soldiers, that difference is decisive. We learned this from the Soviets, Thompson admitted. Their T-34 tank crude by German standards, but they could build 3 T-34 seconds in the time you built 1 Panther. Quantity became quality. Osenberg nodded grimly. We understood this principle with the Panzerfaust. Single shot, disposable, extremely simple. We could produce hundreds of thousands, but by then it was too late. The Americans had a 2-year head start distributing effective anti-tank weapons to infantry. The conversation turned to battlefield employment. Thompson shared operational reports from American infantry units in Europe. What surprised us, he said, was how quickly doctrine evolved. The bazooka wasn't just a weapon, it changed how infantry operated. He pulled out an after-action report from the Battle of the Bulge. Before the bazooka, infantry facing armor had 2 options: call for artillery support or retreat. With bazookas, small units could engage armor independently. It decentralized anti-tank capability down to the squad level. Osenberg read the report, his expression growing darker. This was exactly what we feared when we first analyzed the captured weapon. You didn't just give infantry an anti-tank weapon, you gave them autonomy. A squad with a bazooka could hold a position against armor without support from higher command. Which changed the entire dynamic of armored warfare, Thompson agreed. Our tanks couldn't simply drive through enemy infantry positions anymore. Every foxhole might contain a soldier who could kill a tank. It forced armor to move more cautiously, to require infantry support, to be more vulnerable. The Germans learned this on the Eastern Front, Osenberg said quietly. Soviet anti-tank rifles, though inferior to bazookas, taught us that infantry armor engagement had changed, but we couldn't respond quickly enough. By the time the Panzerschreck was widely distributed, American and British forces had established air superiority, making our armor vulnerable, regardless of infantry anti-tank weapons. One aspect surprised Thompson during his interviews: the German engineers' obsession with maintenance requirements. "Your reports mention repeatedly that the bazooka required minimal maintenance," he noted. "Why was this so significant?" Osenberg's response was immediate: because soldiers in combat are terrible at maintenance. He elaborated: "German doctrine assumed regular cleaning, inspection, and preventive maintenance of all weapons. We designed systems expecting this. The Panzerschreck's electrical firing system, for example, required dry storage and regular battery checks. The optical sights needed careful handling. And soldiers in foxholes didn't do this? Soldiers in foxholes are cold, wet, exhausted, and terrified. They don't meticulously maintain equipment. They use it, abuse it, and expect it to work. Your bazooka accepted this reality. Ours fought against it." He pulled out a field report from the Eastern Front. This report details a Panzerschreck unit in winter conditions. The batteries froze, the optical sights fogged, the electrical connections corroded. Operational readiness dropped to 30% within 2 weeks. What about American bazookas in similar conditions? They had problems too. Rockets failed, tubes cracked, batteries died. But the simplicity of the system meant soldiers could jury-rig solutions, replace batteries with field-expedient power sources, use damaged tubes if they weren't completely destroyed, fire rockets with corroded fins and still achieve kills at close range. The robustness came from simplicity, not quality. Thompson pulled out a document that made Osenberg's face darken, a comparative cost analysis of the two weapons programs. This report estimates, Thompson said, that Germany spent approximately 3 times as much per operational anti-tank kill achieved by Panzerschreck than America spent per bazooka kill. Does that seem accurate? Osenberg calculated mentally. Probably conservative. The Panzerschreck cost more to produce, required more training, had lower operational readiness rates, and was available in smaller numbers. The multiplication of these factors. He trailed off. We estimate you achieved approximately 85,000 vehicle kills with Panzerschreck. We achieved approximately 350,000 with bazookas across all theaters, including Pacific operations against Japanese armor and fortifications. The numbers were devastating. American simplicity had been 4 times more effective than German sophistication. The Panzerfaust changes this calculation, Osenberg noted. As a disposable weapon, it achieved better cost-effectiveness. But it came too late and had much shorter range. True, but it proves the point: when you abandon sophistication for simplicity, results improved dramatically. As the interview concluded, Thompson asked the question that had puzzled American analysts. Why couldn't German engineering culture adapt faster? You identified the problems early. You had competent engineers who understood the issues. What prevented change? Osenberg was silent for a long moment. May I speak about things beyond pure engineering? Please. German technical culture in the 1930 seconds and 40 seconds was shaped by several factors. First, our education system produced engineers trained to optimize, to perfect, to advance the state of the art. We were taught that German engineering was superior precision machinery, advanced chemistry, sophisticated design. This was national pride, technical pride. He continued carefully. Second, the political environment punished admission of foreign superiority. To say the Americans have built something better was to contradict nationalist ideology. Career advancement came from promising improvements, not from recommending copying enemy designs. Political pressure overriding technical judgment, Thompson observed, constantly. When I argued for copying your bazooka directly, I was accused of defeatism. When test results showed problems with our improvements, reporting this accurately was seen as disloyalty. Engineers learned to tell leaders what they wanted to hear rather than what they needed to know. We had some of that too, Thompson admitted, but our system seems to have been more tolerant of pragmatism. Your system valued results over theory. German culture valued theoretical perfection. In peacetime, this produces excellent research. In wartime, he gestured at the ruins visible through the gymnasium windows, you see the results. Thompson shared one final document, a German intelligence assessment from October 1944, predicting the bazooka's limitations. This report, he said, predicted that bazookas would become less effective as German armor improved. Thicker armor on Panthers and Tigers would defeat the shaped charge. The analysis seems sound. Osenberg read it and smiled, bitterly. Technically correct, strategically meaningless. Explain? Yes, frontal armor on late-war German tanks defeated bazookas. But most tank kills are side or rear shots. Most engagements are at ranges under 100 meters. And most importantly, by late 1944, we had so few tanks that it didn't matter what armor they carried. He continued, this report makes the classic error of analyzing weapons in isolation. The bazooka didn't need to penetrate Tiger frontal armor, because American artillery, air power, and combined arms tactics created the conditions for side shots. The weapon was part of a system, not a standalone solution. And the Panzerschreck? We designed it as a standalone superweapon that could penetrate anything, but we couldn't produce enough, distribute them widely, or support soldiers in using them effectively. Perfect penetration capability in insufficient numbers is less effective than adequate penetration in vast numbers. Thompson leaned back. So, what's lesson? Simple is better? Quantity beats quality? No, Osenberg said firmly. Those are oversimplifications. The lesson is more subtle, he thought carefully. The lesson is, optimize for the correct variables. You optimized the bazooka for field effectiveness, ease of use, reliability, producibility, trainability. These variables mattered more than maximum penetration or precision accuracy. You understood what good enough meant in context. We optimized the Panzerschreck for technical capability, maximum penetration, precision, sophistication. In laboratory conditions, it was superior. In field conditions, with average soldiers, limited training time, mass production requirements, and logistical constraints, your simpler weapon was more effective. He met Thompson's eyes. The lesson isn't that simple is always better. It's that you need to understand your operational requirements and optimize for those, even if it means accepting technical compromises. This requires humility, admitting that perfection in one dimension may create failure in others. As Thompson prepared to leave, Osenberg added one final observation. There's something your analysts may not have considered, he said. The bazooka succeeded partly because American military culture was willing to accept casualties in a way German culture wasn't, at least officially. Thompson frowned. Thompson, explain. Your bazooka had minimal training requirements, minimal protection for the operator, and accepted failure rates that we considered unacceptable. Soldiers fired from exposed positions. The weapon encouraged aggressive tactics. This resulted in casualties. But we distributed so many weapons, trained so many soldiers, and accepted these operational risks that the overall effectiveness was higher. We would have demanded better protection, more training, lower failure rates, all things that would have delayed production and reduced availability. He paused. I'm not suggesting American commanders were reckless with soldiers' lives, but American culture accepted a different risk calculus. Get adequate weapons to all soldiers quickly, even if some soldiers are endangered by inadequate training or equipment failures. We wanted to protect each soldier perfectly, which meant fewer soldiers had effective weapons. Thompson considered this. You're saying we accepted distributed small risks to reduce concentrated large risks. Exactly. Better that every squad has a bazooka with a 3% failure rate than having perfect weapons available to only 20% of squads. The mathematics of risk distribution favored widespread deployment of adequate tools over limited deployment of perfect tools. The Technical Intelligence Division's final report on the Bazooka Panzerschreck comparison ran to 347 pages. But the executive summary captured the essential lesson. Comparison of US M9 Bazooka and German Panzerschreck anti-tank weapons technical. Superiority. Panzerschreck demonstrated superior penetration capability, 160 mm versus 100 mm. Better accuracy and more sophisticated engineering. Operational effectiveness, M9. Bazooka achieved approximately 4 times more enemy vehicle kills at 1/3 the cost per kill. Key factor. The M9 was optimized for field utility, ease of use, reliability, producibility, while the Panzerschreck was optimized for technical capability, penetration, precision, sophistication. Conclusion. In military applications, operational effectiveness matters more than technical superiority. Adequate performance available in quantity and distributed widely produces better results than superior performance available in limited quantities. Recommendation. Future U.S. Weapons development should maintain focus on field utility over laboratory performance. However, care must be taken not to oversimplify. Some capabilities require sophisticated engineering. The goal is appropriate optimization for operational requirements, not blanket adoption of simplicity as a principle. The irony of the bazooka story became apparent in the decades following the war. The United States, having learned the value of simple, adequate weapons, gradually abandoned this principle in favor of increasingly sophisticated systems. By the Vietnam War, American infantry were carrying M16 rifles technically superior but notoriously unreliable in field conditions. By the 1982nd, the replacement for the bazooka was the M47 Dragon, a complex, expensive, wire-guided missile system that required extensive training and often failed in combat. It took several more decades and several more conflicts before the military rediscovered the lessons of the bazooka. Modern weapons like the AT-4 and M72 LAW are disposable, simple, and widely distributed, essentially sophisticated descendants of the Panzerfaust, which itself was inspired by the need to simplify after the Panzerschreck's complexity failed. Meanwhile, German weapons development in the post-war period focused on precision and quality. The Leopard tank, H and K, small arms, advanced optics, technical excellence, carefully constrained by hard-learned lessons about operational requirements. Osenberg's final note in his engineering diary, dated October 1945, posed a question that remains relevant. We captured the bazooka in November 1942. We analyzed it completely by December. We understood its principles and could have copied it directly by January 1943. Instead, we spent 18 months developing something technically superior but operationally inferior. Those 18 months cost us perhaps 100,000 casualties soldiers who faced American bazookas without equivalent weapons, or who had access to too few Panzerschrecks too late. The question that haunts me: how many other times in history has technical pride caused operational failure? How many engineers have optimized for the wrong variables, mistaking sophistication for effectiveness? And how many will make the same mistake in the future, because the lesson requires a kind of humility that engineering culture resists? We built a masterpiece. They built a tool. The tool won the war. Today, in the U.S. Army Ordnance Museum, a display case holds 3 weapons side by side: an M1, bazooka, a German Panzerschreck, and a Panzerfaust. The placard reads, "These weapons represent 3 different approaches to the same problem. How to give infantry the ability to defeat armor. The M1 bazooka, optimized for field utility, simple, reliable, mass-produced. Technical performance was adequate rather than optimal. The Panzerschreck optimized for technical capability, powerful, accurate, sophisticated. Field utility was compromised in pursuit of superior performance. The Panzerfaust optimized for radical simplicity, single shot, disposable, extremely basic. Effectiveness through quantity rather than quality. All three achieved significant results. But the Bazooka, introduced first and produced in greatest numbers, had the largest impact on the war. The lesson: in military engineering, the best solution isn't always the most sophisticated one. It's the one that best serves operational requirements, including factors beyond pure performance, ease of use, reliability, trainability, and mass producibility. Sometimes, adequate is better than perfect. Osenberg would have appreciated the irony that the lesson was so simple, yet so difficult to learn.